Okay, we're going to start chapter 4, and this is going to take us in a different direction a little bit because we're going to start talking about trigonometry now. For some people, this is a very hard section, and for some people, it's easy, but there's a lot of terms and terminology to go through here. So let's just look at a few things. The objectives of this section, and it's a lot of them. Recognize and use the vocabulary of angles. We're going to come up with some different types of definitions. Use degree measure, and one that you're not used to, use radian measure. Convert between degrees and radians. Now why we do that? Because the fact that radians is more common used in most functions that we use. Draw angles in standard position. Find coterminal angles. Find the length of a circular arc, and then linear and angular speed. So a lot of different things here. And this is probably one of the easier sections as we go through. Now let's talk about the definitions. Now I left these out and I drew pictures as a slide. If you got the handouts, you have a lot of the definitions down, which is good. An angle is formed by two rays that have a common endpoint. One ray is called the initial side, and the other is terminal side. So I always say an angle is formed where a ray is rotated from its initial side to its terminal side. And that's what an angle is. It's when a ray, here's my initial side, is rotated from the initial side to the terminal side, and it's rotated around its vertex. So if I was looking for a definition, that's what I would be looking for. It's a ray rotated at its vertex from its initial side to its terminal side. Now an angle is in standard position if its vertex is at the origin. Now the origin's right here. Vertex is at, this is a standard position. And this is how we have to use most of our stuff. Of a rectangular coordinate system, and its initial side lies along the positive x-axis. So on here, here's my initial side. Now it doesn't matter which way it rotates. An angle can rotate this way. You notice it looks like, and everybody always called it a little fish, it's alpha or delta, and all these Greek letters we're going to be using as they call them, omega, alpha, and all those. And here's another angle. This is a negative angle, and that's what we're going to talk about next. When we see an initial side and a terminal side in place, there are two kinds of rotations that could have generated the angle. Positive angles are generated by a counterclockwise motion. So if it goes this way, counterclockwise, that's a positive angle. Thus the angle alpha is positive. Negative angles are generated by a clockwise rotation. And thus the angle omega is negative. Now, an angle is called a quadrantal angle if its terminal side lies on the x or y axis. Angle beta is an example of a quadrantal angle. Now, this one rotates a positive degrees, ends up right here. This is 270 degrees because it rotated 3/4 around the circle. So it's 270, and this is a positive quadrantal angle because it falls on the axis. And some of the definitions are ones you're used to. Angles are measured by determining the amount of rotation from the initial side to the terminal side. A complete rotation of the circle is 360 degrees, or written as little degree symbol. An acute angle measures less than 90 degrees. A right angle measures 90 degrees. An obtuse angle measures between 90 and 180, and a straight angle measures 180. So straight angles goes right across. Obtuse is less than 180, bigger than 90. Right is 90, and an acute is less than 90. An angle whose vertex is at the center of a circle is called a central angle. Okay, so if I drew a circle, I'm not very good here. Here's my center, and I'm going to draw an angle out. This is called a central angle. The radian measure of any central angle of a circle is the length of the intercepted arc divided by the circle's radius. So the radian measure is taking this arc divided by my radius of my circle. That's going to give me my radian measure. Now there's a big definition. 1 radian is the measure of the central angle, so the measure of this angle, when central angle of a circle that intercepts the arc will equal in length to the radius of the circle. So in other words, 1 radian, 1 rad output, is the same when the radius and the arc length are the same. So consider an arc length of length s. So here's my arc length, and the circle radius r. The measure of the central angle theta that intercepts the arc is theta is equal to s over r. So s divided by r is my radian measure. Take your arc length divided by your radius, it gives me a radian measure. So let's look at one. The central angle theta in a circle whose radius is 12 feet intercepts the arc that length of 42 feet. What is the radian measure? So really, in other words, the arc length is 42 and the radius is 12, so we're going to divide that out, and I might have here 3 is 36.5 radians. Now you could put RAD. There's no really symbol for that, but RAD would put it. Usually, if they don't have a symbol and they represent an angle on here, they do 3.5. They know it's in radians. Now, how do we convert? Using the basic relationship, pi radians is equal to 180. That's very important. Pi radians. So in other words, if you think of a circle, this is a very small circle, and I split the circle into fours, I'm going to say this is 0, 90 degrees, 180 degrees, 270, and then back over here would be 360. We can still start with 0. Now this is in radians, this is going to be pi over 2, pi, 3 pi over 2, 2 pi, and with that too, as we go through, it gives us our radian measure around the circle. So 360 and 2 pi are the same. Pi and 180 are the same. To convert 2 degrees to radians, multiply degrees by the pi radians over 180. So to convert from degrees to radians, we're going to multiply by pi over 180. To convert from radians to degrees, we're going to multiply by 180 over pi. Okay, so I'm just going to turn something off here real quick. I'm going to quit Dropbox right now. Okay, so now let's look at some problems here. Let's convert each of these angles to degrees, to radians. So what we're going to do is we're going to say 60 degrees. We're going to multiply by pi over 180. Now 60 I can put over 1 and I cancel off. 60 goes into 183 times. So pi over 3 radians. Now notice that most of the time you have radians, you're going to have a pi measure there. But not always as you go through. 270, we're going to multiply by pi over 180. Well, that goes in both of those. 90 goes in both of those. We have 3 and 2. And if we work it out, 90 goes in both of them, so we get 3 pi over 2 radians. Now, I didn't put the word radians because I don't have to. If I don't put any symbol. Notice on degrees, you put a degree symbol. On radians, you don't put anything. Negative 300 degrees, same thing. We're going to multiply by pi over 180. Now, I don't know which number goes in there easiest. I guess dragging my mouse here. Let's try 30. 30 would be 10 and 6. We can keep going down. 2 goes into both of those, 5 and 3. So this would be a negative 5 pi over 3, and that's in radians. Now let's go the other way. Let's convert pi over 4 radians into degrees. Well, what we're going to do is follow our rule. To convert from radians to degrees, we're going to take pi over 4 times 180 over pi. Pi's will cancel. 4 goes into that 180 45 times. So we're going to have 45 degrees. Negative 4 pi over 3 times 180 over pi. 60. So it's negative 240 degrees. Now notice this one says 6 radians. There's no symbol with it like pi or anything, but it's still in radians. So we're going to take 6 times 180 over pi, which we're going to get, I'm going to write it out as 1080 over pi degrees. Might get a decimal answer. You might want to divide that out and get a decimal answer, but that's okay too. Now drawing angles in standard position. The figure illustrates that when the terminal side makes one full revolution, it forms an angle whose radian measure is 2 pi. So all the ways around the circle is 2 pi. The figure shows the quadrantal angles of 3/4 pi, 3/4, 1/2, and 1/4 of the revolution. So 3/4 of the way around the circle is 3 pi over 2, and I kind of drew that earlier. Halfways around the circle is pi, and 1/4 of a way around the circle is pi over 2. So we get our 4 quadrantal angles: pi over 2, pi, 3 pi over 2, and 2 pi. You will have to memorize these values and know how to find them. Now I just left some of these out here to look at. Draw and label angle in standard position. Okay, so here says theta is equal to a negative pi over 4. Well, negative means it's going backwards or clockwise. Pi over 4. Well, pi over 4 is, here's pi over 2. Negative pi over 2. This is a negative pi over 2. Well, pi over 4 is half of that. And it's negative, so halfway is between here. So here's my initial side start here. Here's my vertex. And I'll rotate it halfway, draw my angle. So this value right here is a negative pi over 4. Now 3 pi over 2. Notice it's positive. 3 pi over 4, I mean. 3 pi over 4 is close to pi over 4. Or 4 pi over 4, which is pi. Pi is over here. This is pi, which is equivalent to 4 pi over 4. 4 will cancel off, give me pi. This is pi over 2, which is equivalent to 2 pi over 4. Well, if I'm looking at 3 pi over 4, it would be right in the middle of these two. So 3 pi over 4 would be right in the middle here. So I drew my angle. Initial side here, draw along. And sometimes what I need to do is have to think about these, and I say, well, if I don't remember where it fits, I might want to do is say, okay, I'm going to change this to degrees to see where it is. Okay, 135 degrees. Well, we know our circles: 0, 90, 180, 270. Well, 135 is right here. That's another way of looking at how to get to those angles to see where they're at. Negative 7 pi over 4. Let's do that one this way. Negative, I don't care, hurt that. So we get negative 7 pi over 4. I'm going to change it to degrees just to see where we're at. 45 goes, oh, not pi, sorry. Pi's will cancel off. 4 go in here 45 times. So there's a negative 315 degrees. Okay? So, and we're looking at negative, so we're going to start with your initial side. We're going to rotate negative 315. Well, here's a negative 270. We're going to go a little bit further than that, but this is a negative 360, so we're not going to go this far, so negative 315 would be right in here. So this would be a negative 7 pi over 4. Last one, 13 pi over 4. Well, I do this one a little different. We're going to change it to degrees again. Might be a little harder here. This is 45. And now 45 times 13. Well, I don't know what that is. Let's see. We'll work it out. 45 times 13, 135, 45, 585. Okay, so what 585 means, okay, it's going to go all the ways around. That's 360. One way around the circle. Now if I add on another 225, I would get the 585, right? So what we have here is, I'm just going to draw a different circle here, draw a different line. It goes like this, starts here, goes all the way around once, that's 360, keeps going around, here's another 180, so that's at 540, we're not quite there, so we're going to keep going till we get here. So it's like a complete circle and another ways around to get to 13 pi over 4. So it's a little bit more than a complete circle. Okay, now degree and radian measures. You'll notice on here in the figure below, each angle is in the standard position. So the initial side lies on the positive x-axis. So you'll notice on here, going positive, we get 0, 30, 45, 60, 90, 120, 135, 150, 180. And with it, we have its radian measure that goes with each one of those. And over here, negatives. As you go on the negative radian measure. Now a few more definitions here. Two angles with the same initial and terminal size but possibly different rotations are called coterminal angles. Increasing or decreasing the degree measure of an angle in standard position by an integer multiple of 360 results in a coterminal angle. Thus an angle of theta is coterminal with angles of theta plus or minus 360k, where k is the integer. Increasing or decreasing the radian measure of an angle by an integer multiple of 2 pi results in a coterminal angle. Thus, an angle of theta radians is coterminal with angles of 0 plus or minus 2 pi k. What does that mean? That means if I add 360 to a degree measure, it's the same angle, same position of the angle, but different measure because it's one complete revolution more. Now, if it's a radian measure, I don't add 360 degrees. I would add 2 pi radians to get a coterminal angle. So let's look at this one. It says, okay, I got 400 degrees. It says, assume the following angles are in standard position. Find a positive angle less than 360 that is coterminal. Well, I'm at 400 degrees. So what I'm going to do is you either can subtract or add. So I'm going to subtract 360. One complete circle. If I do that, I'm going to get 40 degrees. So 400 degree angle and a 40 degree angle are the same position angle. They look the same, but one's one complete revolution less. Now on here I got a negative 135 degrees. So now what I'm going to do on here, I'm going to add 360. So if I add 360, I'm going to get 225 degrees. So therefore, another positive angle that's less than 360 would be a coterminal angle. Coterminal means adding and subtracting 360. Now we could do that to radians too, but now what we're going to do with radians is a little harder to do. Here we're going to subtract or add. Now 13 pi over 5 is bigger than 2 pi, so we're going to subtract 2 pi. Now the problem here, we're going to subtract 2 pi over 1 with fractions. We have to get a common denominator, which would be 5 here. So I'm going to make this 10 pi over 5, which is the same as 2 pi. 13 pi minus 10 pi is 3 pi over 5. And that angle, radian measure, is less than 2 pi, so we're okay with that. Now over here, negative pi over 15. That's a negative angle, so what we have to do is add 2 pi. And again, common denominator, 15, so we're going to change this to 30 pi over 15. So 30 pi minus pi is 29 pi over 15. These two angles are the same position, but different measures. Now length of an arc. Let r be the radius of a circle and theta be the non-negative radian measure, key here, radian measure of a central angle of the circle. The length of an arc intercepted by a central angle is equal to, arc length is equal to radius times theta. Should not be a surprise formula because a second ago when we did radian measure we said S over R. So this is the same formula just written a different way. So what this formula says is to find my arc length I need to take my radius times my angle when it's in radians. So for example it says a circle has a radius of 6 inches. Find the length of the arc intersected by the central angle 45 degrees. Express your length in terms of pi, then round your answers to 2 decimal spots. I'm not going to worry about the 2 decimal spots right now because I know you can do that. We first convert 45 degrees to radians, so we're going to multiply 45 degrees by pi over 180. And we're going to get that 45 degrees is pi over 4. Now if we're going to do our arc length, we're going to take our radius, 6 times pi over 4. So we're going to get 6 pi over 4, which is 3 pi over 2. Now, if I work that out, I will put the 2 decimals. I'm going to get my calculator out here, if I can. Let that start up for a second here. Okay, now we're going to go back to our problem here where it says 3 pi over 2. So we're going to go 3 times pi divided by 2. Enter, and we get 3 pi over 2. So we're going to go Control, Enter. So 4.71. So this is approximately 4.71 inches. That's my arc length. Now, to the harder form is that people have a tough time with. I don't know. If a point is in motion of on a circle and the radius r through an angle theta radians, again, we're in radians, in time t, then it's linear speed. Linear speed is v, is distance, arc length, divided by time. Distance divided by time. Where s is the arc length, given by s equals r theta, and its angular speed. Now, its angular speed is w is theta divided by time. Linear speed is distance divided by time. Angular speed is angle divided by time. The linear speed of a point, a distance r from the center of the rotation, is given by this. Linear speed is equal to r times your angular speed, where r is your angular speed in radians per unit of time. So let's look at this. Long before iPods that hold thousands of songs and play them with superior audio quality, individual songs delivered on 75 RPMs and 45 RPM circular records. A 45 RPM record has an angular speed of 45 revolutions per minute. Find the linear speed point where the needle is 1.5 from the center. So it says here, before finding linear speed, before applying the formula of linear speed equals r times your angular speed, we need to express angular speed in terms of radians per second, because we're not in angular speed right now. We're in revolutions per minute, not radians per minute. Okay, so what we're going to do is we're going to say, okay, right now it's 45 revolutions. Okay, and every revolution is 2 pi. Okay, so right now, because I remember our whole circle is 2 pi, so this is 90 pi radians per, and this is this minute. Okay, wait a minute, we want it in, it says per second. Oh, okay, yeah, we have to change that minutes now. We're going to put 1 minute is 60 seconds, little conversion from science now. We're going to divide that out, and 60 goes into 90, 0, so it's 3 pi over 2, and that will be radians per second. So that's my angular speed, 3 pi over 2 radians per second. So now what we need to do is go in here, okay, and we have it per second, so we're going to leave it per second here. Find the linear speed in inches per minute. Well, wait a minute, now it changed on us. The 45 record has an angular speed of 45 revolutions per minute. The linear speed is, which we said earlier, 90 radians per minute, at a point where the needle is 1.5 inches from the record center. The linear speed now, if we wanted to find the linear speed, is going to be your radius, which is 1.5, times my angular speed, which is 90 pi. So if I do that, it's 135 pi radians, or not radians, now it's inches per minute. And now they didn't ask us to do it in seconds, so inches per minute. I could multiply it out if I want to, but that'd be a pretty good answer right now. Now what I like you to do for handing purposes is on page 5, let's do page 505, 506, let's go. We want to do number 83. and 99. These will be harder problems, so you might have to stop in and talk to me. Thanks.